We're live. Hello and welcome, ladies and gentlemen. Good afternoon. It's 5 p.m. Central European Time. We're at the second HIGHVOLT Web Talk here, live from Dresden. My name is Florian Schwarz. This is Uwe Kaltenborn. Uwe, good afternoon.
Good afternoon.
We had a wonderful feedback last week when we had our first web talk. What was the feedback?
The feedback was really great because we had more than 200 participants in chat.
Great.
Plus over 800 participants who have seen the live stream. Altogether more than 1,000 people which have seen the live stream at all in the last 1 week.
Mm-hmm.
So therefore the expectation is now raised to a very high level, and we will see what happens today.
And we are very glad, and of course you can participate at this web talk. We are giving you the address. You can go in the chat with us. In a minute I explain you the experts that we have here. But Uwe, at HIGHVOLT here you're the Director of Business Development, but we are in this big testing hall. What do we see in the background?
Yeah, so to have the comparison to the last time, so we have in the back directly from us. Maybe we can switch to the total view. Then we see in the back the impulse water system. Today we have combined that with some voltage dividers, capacitive dividers, and we have a multiple shopping gap there on the left side, which is also very impressive device manufactured here last week.
And of course, in the next live minutes, we can show all this again. Then we have different camera perspectives. Therefore, one thing that you wanted to be.
Yeah, we have the topic of today, partial discharges. So therefore, we are to discharges.
And this is the perfect written dialogue, as you can imagine. Of course, I'm prepared. Here is my answer. So far, a little explanation what we are talking about today. Thank you very much for this. And now I can present you our experts we are discussing this afternoon. First of all, live from Berlin, we are connected with him, Professor Ronald Plath. He is a professor for high voltage engineering. His research activities are PD, of course, also on site, dielectric diagnostic, space charge measurement, and he's member of SIGRE. Welcome, hello to Berlin.
Hello from Berlin.
Then on the other side, one chair next to me is Eric Winkelmann. He's a senior test floor engineer at HV. He studied in Dresden. He holds several patents in the field of PD measurements. And his focus is the use of real-time signal processing and machine learning. Good afternoon, Eric.
Thank you very much. Good
Hello. And last but not least, I have Dr. Alexander Gretke next to me. He's from Omicron. He's the area sales manager and, of course, a transformer expert. Studied at University of Technology in Berlin. He's a senior member of IEEE and involved in the SIGRE D1 and A2. And he wrote more than 100 technical and scientific publications, so quite a writer. Alexander, we're coming to your first statement this afternoon. Over the last 20 years, the digital measurement significantly demystified the practical application of partial discharge measurement, and it increased its acceptance. Is the measurement the result? I guess no. What are the difficulties for the interpretation of PD measurements?
The partial discharge is that which is specific for each electrical equipment has different aspects of partial discharge. So the result, the number, the figure is not really the information. It's more than that. It's the interpretation. What does the measured value really mean for that specific kind of equipment? So it's more than a number. It's also the interpretation, what the number really means for the insulation system, which is under investigation.
We discuss about all this, of course. In the beginning, we always do a round of statements. I come to Eric Winkelmann. As in all branches of industry right now, digitization and data science will dominate, of course, the next decade, that's for sure, and especially in partial discharge measurements. So digital handling of analog data has improved in the last years. Will that influence also the way how to measure, how often to measure, and maybe very important, how will that make the interpretation of results easier?
Yeah, thank you. Maybe to give a short introduction, I think everybody has heard of buzzwords, so-called buzzwords like big data or artificial intelligence. And the most successful companies and also business models do base on these models. And for example, Google, Microsoft, or the Chinese equivalent Tencent. And in other fields of applications like biomedicine, speech recognition, or the interpretation of seismic events like earthquakes, all this has been done very successfully and generated knowledge. And knowledge meaning in the sense of understanding relations between processes or even interactions between those processes. And if you understand all these processes, you are able to model this behavior. And if you model it, now the big data thinking comes and you have a lot of measured data, then you are able to do what everybody wants to know, which is almost the same question for all those topics, is where does the signal come from, which I measure? How did it look like as it was at the origin? What was the way it has traveled through? So how can I describe the way from the signal origin to my point? And if you can do all this, you can even predict how will this system behave in the future. And as I told before, it's always the same question. And all this has successfully been done for biomedicine, speech recognition. Everybody knows the little Alexa or whatever. And only in the field of electrotechnics, something like this is not really present, not in this state. So I believe strongly that we will see some approaches there and also development in the future.
Very interesting sight into the future. We are going to Berlin to Professor Ronald Plath. The measurement of partial discharges is not only a proven but also the only established method to detect and locate singular weak points in the electric insulation to prevent, of course, catastrophic failures in the grid. PD measurement, black magic or effective correlation of root cause and physical effect?
Yes, when I started with PD measurements as a young student, it frequently appeared to me as black magic because it is complex. If you use two different instruments, you will get usually two different results. This has all changed in the meantime, and we now, I would agree to Dr. Kretke, due to strong impact of digital processing, we have a better, clearer view on the signals, and we better understand the physics in behind. And I hope that the audience will see PD as a very important tool for insulation diagnostics and not anymore as some kind of magic.
I think also at this point, sometimes during our presentation, we have the possibility to bring in some slides also. Uwe is the responsible for this then, and we do this after the next question, Uwe, or already? Because I have another question for Ronald Plath. What kind of effects or defects can be described or detected in insulation systems?
Practically every single weak spots in the insulation system, whether it is internally to the insulation, which is of course of major importance to prevent from weak spots inside the insulation system. And that causes also problems that we have always to deal with external effects like noise, interference, and corona discharges, which we also call outer partial discharge, that usually superimposed to our internal signals that are weak, very small. That has to be taken into account. And finally, we know that, like Mr. Wiedemann already mentioned, that when we have internal PD, it will finally lead to breakdown, at least in polymeric insulated systems. And so we have to prevent by sensitive measurement and localization of such defects.
Mm-hmm. Therefore, the question then, Uwe, please.
Maybe I hope now the mic is working properly. So in that way, I have some examples prepared. I hope we can see them. So can you please show the slides I have prepared? Right, so this is a typical example where you can see partial discharges where you have voids in a GIS spacer, very typical effect. So the interesting point here is that you have exactly 2 voids. Another topic which is very typically a problem we face here with our high voltage test equipment, that you have scratches, as you can see on the upper left side in our big shielding electrodes, and there's always then the question how to detect where it is, and you see it first electrically with the electrical pattern, but then we also have a UV camera to see where we have this defect and in which way we can also solve the problem. Another very much important issue is also that the typical way is that you always look to the high voltage potential as the root cause for any discharge. Nevertheless, this is a very nice example that the fans, which is very close to the test equipment, could be also the source, and therefore the grounding electrode has also to be under control.
Thank you, Uwe, for the slides. Typical patterns and defects. Alexander Gretke, again, to this topic, what kind of effects and defects can be described and detected in insulation systems?
Yeah, we can, as Ronald said, we can see, let's say, cracks. We can have parts that don't belong to the insulation and are got into let's say paper layers in between, something like this. Everything which is really disturbing the designed distribution of the electrical field inside the insulation, because the grading of the insulation is the most important part of the electrical and especially the high voltage systems, and that's why we have to look for the weakest link, because this is where equipment may fail. So this is that's more or less the only chance that we have to detect very, very small defects which can develop into some catastrophic failure, as you said it before.
Is it the famous look for the needle in the high mountain?
Yeah, that's it. Especially, and the problem is that we are looking for the falling needle in the middle of a highway. So all the signals typically are way higher than the signals we have to look for.
Okay.
That's one of the major challenges.
Acoustical, thermal, and then. Absolutely. And do you have the impression that the development is going to be faster and faster? Are you coming to the point where you are really happy and satisfied with the test measurements?
Especially the digital technology really developed into a way that we have much better chances than at least 10 years ago to find spots to get small signals out of the background noise level. So I think the technical development over the last years was remarkable, and I think that really gave us a much better feeling in being sure that nothing is wrong with the insulation.
And that's also, of course, a purpose of this talk. It's nice that you connect us and you join us every Wednesday. Now we exactly talk about this branch, this speciality, and of course also the movement of the technology, because there are different technologies, Eric. And are they still needed in the future, or will we have one dominant technology that comes out?
Okay, if you say different technologies, this is really a broad field, I would say. So you have, of course, electrical conventional PD measurement everybody uses for quality assurance and as a contract tool. So to say 10 PC or something is a good value and everything above is a problem or below is good. Then you have the acoustical measurements. You have the UHF. You have the optical, what you also mentioned before, the optical UV cameras, the ultraviolet. Then you have the DGA, so what gases are dissolved in on our oil. Then we have fiber optic tools, so distributed acoustical sensing, or even measuring directly the PD in a joint with fiber optics, which is, I think, Professor Blatt also working on in Berlin. And in my opinion, so from my test floor view, here in the laboratory we work with oil-filled components mostly, so this is my experience. We need them almost all, so, but I have to say that I'm, in contrast to the others here, I'm not so much a friend of interpreting the pattern and saying, okay, this picture belongs to this failure or error or whatever, because at the end, if you have like a 25-ton high voltage component, you don't want to know if it's a void or not. You want to know where it is if it's a problem. So what I do is I do an electrical measurement. I have a value which is in the contract, and if I'm above, I have a problem and I have to solve it. So in the next step, what I want to know is it inside the component or outside? I could use UHF for this. So UHF is very sensitive to PD which are internally. And if I know this, I have to decide, do I want to repair or not? And if I want to repair, I need to know where it is. And then we are at the acoustical or maybe UHF localization. So and if you think of monitoring,
yes,
you can do whatever you want and just do a trend analysis. So more or less you have a start value, which you say it's good. And then you say if it's 5 times higher, it's bad, or maybe if it's 5 times higher within 1 day, it's very bad. So this is more or less what I would say to the different technologies. And to answer your question in short, yes, they are all needed.
They are all needed, all the technologies, but for you, of course, being on the practical side, being every day here in the test lab, is it a wish to have one dominant technology at the end, or are you happy with having these different technologies?
I think we need these different technologies because of the advantages and disadvantages. So the one technique is to quantize more or less the PD, to make it comparable. One technique is for the localization. Another one has another approach. So you, in the end, need different techniques. Okay. There's no technique, in my point of view, which solves all these problems.
This one side is the different forms of technology, different technologies. Alexander, the suppliers, of course, another question. Will we see more supplier of PD measurement equipment in the market or less in the next, let's say, 10 years?
Yeah, that's a good question. I mean, with the quickly developing possibilities of, let's say, also low-cost kind of technology for integrated circuits and stuff, there are more startups coming up, but typically these have a background of electronic development, and the strength of the, let's say, established players in the market is that they have the combination of being able to make a strict development and electronic development, and combining that with the market needs, and this means understanding the needs of the application. So you have to know the application know-how. What does the cable manufacturer need? What is the need for somebody testing cables in the field, transformers, dry type, oil filled, whatsoever? This is the one side, and the other side is developing the right equipment for that specific purpose, and then bringing the needs and the technology together with the application know-how, because very often people who have to test equipment are not familiar with that much with the technology, and otherwise the instrument manufacturers do not know everything about the needs of the field, and you have to integrate this. And this is very tricky for startups. Otherwise, they may have come up with good solutions. Let's see. But I think especially as there are new applications, maybe we talk about later about that. I think especially the developed application suppliers are in the lead at the moment. I don't think that there are that many new technologies, because the application is the understanding of the application is the key.
Is key. Okay. Of course, the understanding is here also a topic that we try to develop, and we are in between our second web talk here live from Dresden, which we do every Wednesday, and together with Dr. Uwe Kaltenborn, he's collecting the questions that, of course, you can ask from all over the world to our topic today. Uwe, are there some questions coming in, I guess, per mail or per chat?
per chat. We have a lot of interesting questions. I will adapt.
We have to just check the sound again at Uwe, because something with the microphone is in the second not working, which is no problem because we can repeat, of course, all the questions. You can post your questions during here the session, our second web talk, and we try to now, Uwe, take a try because as we are broadcasting to all over the world, it would be too loud to scream, really. I mean, we can hear all over Dresden, but
so I don't know, is the sound now correct?
We're gonna check. Is it fine?
Yeah, now it's fine. So
excellent. The questions from today's topic.
Yeah, I will divide the questions into two parts. One part will be the very practical questions, and these practical questions we will answer in the second part, or I hope that our experts can answer that. Nevertheless, I would like to focus on some specific questions to PD measurements as such. There is one major topic which was questioned several times, and that is related to the standard. Does the actual standard, with the limitation of bandwidth of PD measurements, do also limit the possibility in PD diagnostics and digital signal processing? I think that's a question we can direct also to Berlin, and maybe Alex, you will be also able to answer that, because this is something you both handle all the time with the standardization work.
Professor Blatt.
Yes. First of all, I would like to go back to Mr. Wiedemann's statement, and I think we have to clearly distinguish for the audience in between two application fields. One is the lab, where we usually can suppress any noise, any interferences by Faraday cage, by line filters, etc. And we usually do not face a problem to have very sophisticated systems to get the best possible signal-to-noise ratio sensitivity in case of checking IC or IEEE thresholds given in the standards. So this is one field of application, and to be honest, I think this is from the commercial available system quite well solved, and I think we have only to add up specific devices like mentioned before, like UHF for suppressing corona or for acoustic sensitivity improvements to localize acoustic signals. But it becomes a complete different field when we leave the laboratory and we go in the field, and more, and I think more than nearly 2 decades, we do not hesitate anymore to leave our labs and go on site and do partial discharge measurements in the field. And then, of course, every sophistication is needed to get best possible sensitivity and selectivity, which means that we have to distinguish, as mentioned before, whether the PD detected or the signal detected is harmful for our equipment or not. And that is much, much more difficult in the field than in the well-screened laboratory. So to my mind, the IC bandwidth limited are mainly due to the idea that we can quantify apparent charge better as long as we can stuck with the capacitance, capacitive equivalent circuit that you showed in the slides in the beginning of our meeting. As long as we want to deal with charges, with apparent charges, I think there's no way out than to leave the frequency low in the lab, and that is not a real problem, usually because of low noise situation. When it comes to the on-site measurements, of course, it's a completely different situation. We have no standards that claim certain thresholds not to beaten, and we have a completely different task. We have to understand what's going on. And for this purpose, I wouldn't agree to Mr. Wiedemann in one aspect. The patterns may not be perfectly identify the root cause of some partial discharge, but they help a lot. They help a lot to distinguish in between interferences and the PD of interest. So this major separation is of very good by partial discharge pattern, at least for AC measurements. Maybe we come to DC later.
Yeah.
But we need their different frequency ranges to suppress the noise of the environment. And then low frequency measurements are extremely difficult. So that is one of the reasons we since long use up to 2 gigahertz or more to get best possible corona suppression, for example.
Professor
But
Plath,
that is not enough.
I can give Herr Winkelmann the opportunity to give a replique.
No. I think Professor Plath is right, and that's not actually what I really said. I said that at the end, if I have a pattern, it doesn't matter for me if it's a void discharge or a surface discharge. If I have a certain value which is too high, then I have a problem contractually, and I have to solve it. Of course, another question is going in the field, monitoring and so on, and using the pattern for separation. So I'm totally agreeing with Professor Plath that for separation of different sources, the pattern can be, of course, very helpful, and you can rely on the typical corona pattern. So I have to say so. So everybody knows that corona is clearly distinguishable between every pattern. But also, I have to say, from my test flow point of view, I saw a lot of pattern which looked like the typical book void or surface discharge, and then it was just a letter standing too close to the test object or something else. So and nobody could explain why this is a void at the end. But to say so, I have to confirm this.
Alexander Kretke.
There's 2 remarks to the question and to the idea about it. It's just a few years ago since we broadened the allowed frequencies. So up to 2008, I think, the allowed upper frequency corner anyway was 500 kilohertz, and we broadened that to 1,000 and that's for the lab. So we tried to come closer to between narrow and wideband measurements on the one side. The other side is when it comes to pattern recognition and localization, the idea is very different. You ask for which is the dominant technology or let's say the standard to apply. When you have to do something comparable. If you want to apply a value to say this is good, this is not good, this goes through to the test or not, then you have to do something. But this works in the lab, and it's not really applicable to the field, because the question for the field engineer is a different one. I have to make a risk assessment. Can I repair the transformer on site, or do I have to ship it back? So this means I need the pattern and I need the localization to bring all this information together. It's complementary. And then it's not the value, is it 100 or 1,000 picocoulomb? It's what kind of defect is it, where is it, and what does that mean for my specific asset? And then I have to do the follow-up. Repair on site, drain the oil, or just lower the oil level, or do I have to, when it comes to cable PD, do I have to open a Kudam somewhere or not? So that's really, and this is the one that's information that supports, the PD is the information that supports the decision maker in seeing what the next step for this equipment is.
And
that's the point.
Uwe, that we have one short replique of Professor Plath.
A short remark.
Short remark.
I think we have to get rid of a common misunderstanding in the field of PD measurements. We know, and at least the expert know much more that can be simplified to a value, a threshold value in picocoulombs. The problem with standards is that we still think in terms of breakdown voltages, let's say, yes or no. But no one of the experts would agree that 5.0 picocoulomb is dangerous and 4.9 is non-dangerous to the insulation system. So we since long we discuss the problem that we cannot bring into the standards a more complex interpretation-based rule, because there we will find no common ground. So we stuck with the number, with the picocoulombs. That is a very general problem that has to be understood by the application engineers, that we are not limited to. But if we do acceptance testing, we need a number. Otherwise, we get no threshold or no limit within standards. That is very important to me.
Thank you for this remark. Uwe, one last question out of this round, then we go in the second part.
No, I think that fits very well. So the phase-resolved PD pattern contains a lot of information about the different phenomena. And there's a question I would like to reformulate in that way. In which way we have a common or standardized database of these phenomena to make the interpretation easier, and in which way then also big data can help in that direction.
Question to all three
To
of you?
all three.
Okay. Short answer. Who wants to start? Okay.
Short is,
Yeah.
will be difficult in this case. To my mind, so I followed more than 30 years the development of PD measurement in general, and especially pattern recognition, of course, is high interest because it gives us a dream that we can get rid of experts and find simple algorithms that can do the job. And I'm personally not perfectly convinced, because when I work as a test engineer, I take into account not only the pattern or not only the magnitude. I take a lot of things into account. Maybe the ladder that was mentioned in the lab that stands still in the corner that's not connected to ground potential. All such things impact my measurement, and that's the reason I would a little bit be not too optimistic after decades that we find the holy grail in pattern recognition, because we need a very sophisticated understanding before we can trust in patterns. And as a solely input of data, I think we are far from the general solution that pattern is the overall, let's say, problem solver. I don't think so.
Please.
Pattern recognition is very much depending on the type of the system and the type of the equipment. So we have very well defined pattern databases for gas-insulated switchgear and components. We have quite well established database for rotating machinery, for generators. But for example, for oil-filled transformers, that's quite more tricky, and also for cables. That's why it depends on the type of the object. And the other thing is then this kind of interpretation. The next question is, what does that mean for the risk for the assistant? Then the location comes into place. The same effect in one part of the equipment can be very dangerous, and the same effect with even maybe with a higher amplitude is not dangerous at that spot. So there's more information than just the pattern. So the pattern has to be seen together in conjunction with the localization and the kind of installation system.
Erik?
Yeah, but maybe to follow up on this conversion, still at the end, if you have distributed elements like in a transformer or in a cable, you look on a value which is apparent charge and maybe with a 10% chance true. So the only thing maybe you know is that it's bigger. Maybe it's bigger. Maybe even it's bigger. That's the only thing you know at the origin. So still at the end, if you want to look at the pattern and to do like a acoustical localization, you have to have a value where you start your acoustical localization. So if you have 10 PC but the origin it's 200, and you want to localize starting with 100 PC, then there are 90 PC missing, and you will not do this. So you will look at the pattern, but you will not do the localization. But you don't know anything about the PD behavior at the origin.
Okay.
And this is for every distributed element device the same problem. And if I read the IEC standard, at the end in the annex it is written it is not suitable for elements with distributed elements, so transformers and cables.
We're coming to this, and so
and rotating machines and everything which really exists in the reality. Yeah?
I understand that the search of the Holy Grail continues, of course, in this subject, but this is nice that we can talk about it. And we are starting in the second round. Of course, you can actually still chat with us and give your questions to this talk. Alexander Kretke, the actual standard for PD measurements is the IEC 60270. Is the standard reflecting the effective needs for the field work?
No, this standard is the baseline for all things to compare results. So this is a lab testing standard. This is not intended to be used in the field, and it's typically due to its quite strict boundary conditions. It's very hard to apply it on the field, and the question in the field is, as said, the different question to be answered as compared to the lab. In the lab, I want to know, do I pass the test or not? In the field, the question is, what's next? What do I have to do as a decision maker, as an asset manager with the equipment? What are the steps? This is just an information that helps me to support my decision making. And one last remark to the pattern recognition, to wave the flag for organizations like IEC and CGRE. There are a lot of working groups since decades who collect databases with known pattern. But one of the things is, and that's affecting all of us, the failure rate of high voltage equipment is quite low. So you would need a lot of failing equipment with PD measurements to get a larger database. A lot of database content is made in laboratory experiments at universities. Luckily, we don't have that high failure rate for high voltage equipment, and that's why we also don't have that much large database of failed equipment. And that's one of the things we are happy about it, but it's hindering the broadening of PD database.
You have a remark to this, Eric?
I just
before I come to Berlin?
Just maybe one question. If you say the IEC standard is for comparable results in the laboratory, what are your expectations? Which percentage I can achieve with this standard? So if I compare different measuring devices with different measuring frequencies, one analog, one digital, so one MPD, for example, and another one from the market. So if I take all these 50 measuring devices, all of them are IEC conform, do you think that they will do a good job in the laboratory? Or what do you expect for a percentage of the error they have?
It's very hard to say. I think that the leading equipments in the market are quite comparable. It depends a little bit. But in general, the standard is quite strict. But even though, if you develop the insights of the instrument, you still have quite a degree of freedom in interpreting values and bringing that to the result. But my expectation would be that it is not too far away from each other. And the other thing is that the acceptance values are based on experience over the last decades. And change in equipment, change in design, change in different development tools can also may also change the acceptance levels. And that for transformers, for the moment, the trend is clearly that we lower the acceptance values. Things which have been accepted for years are unacceptable now.
Yeah.
Maybe one comment to standards. I think it is worth to mention that the IEC 60270 not only deals with measurements, but it deals also with the equipment itself, with calibrators and the instruments. And there's a simple answer to Mr. Wiedemann. How many PD measurement systems on the market are already type tested according to the standard? What do you think?
I think at least 10, 12.
I know only 2.
And I know directly 3, so I would look for another 7. I have to say.
Interesting. we can make a battle here.
No, to Mr. Wiedemann is fully correct that the standard limits itself in, let's say, simple capacitive circuits. That is of high importance to understand, and that is exactly the reason. If it comes to distributed elements like transformer windings or machines or even with cables, that you have to know a lot about the physics in behind to know the limits of the standard, to understand it and to apply it in a correct manner. And I think if you simply say you go down to 10 kilohertz measuring frequency, which no one tends to do, of course, then everything behaves capacitive, and then our life would be much easier. But you want to, I want to, and so we have to stuck with a complex overall situation and do the best to make the best out of it.
Mm-hmm. One last remark.
Maybe just a last point to the pattern recognition topic, just to make a compare with something else. So if you think, like, for example, you want to measure the sunlight, you would never take pictures of the sun and try to compare them more. Maybe the approach for for pattern recognition is just not the right one, and that's the reason why maybe many years gone away and nobody is able to do this in a good manner. That's just what I want the audience to think about. So.
We leave this and stand this here. Just jumping to Berlin to Professor Plath regarding research. You are the convener of the SIGRE VW163 PD measurements. What is it to expect for the academic and research world in the next years to come?
The problem that we face with DC is, of course, that we have no phase that we are used to have with AC testing. And that exactly excludes the classical partial discharge pattern that we are showing in a histogram with respect to the AC phase, because there's no phase. So we have to look for different evaluation approaches. And one which comes from the AC world is the so-called pulse sequence analysis. In the moment, to the knowledge of our international working group, it's the only procedure to evaluate sequences of partial discharges appearing at DC. And what we can expect is two things to my mind. One is the demand for high selectivity is dramatically increased for DC testing, simply for the reason that some internal failures appear, let's say, every 1 hour. I heard from a company in Switzerland that they searched a PD defect that appeared every 43 hours. And you can imagine that statistics based on such long breaks in between two pulses is a nightmare for our test engineers. And we will never look for tests that will last 3 weeks for a simple PD test. So we are barely looking for high selectivity. And that brings me back to the idea to combine the several, let's say, physical appearances of partial discharge: electromagnetic, light, acoustic, mechanical, chemical. Maybe we can go only further if we combine them. But this, of course, increases effort and costs and time to use it and to apply it properly. And but this is, to my mind, in the moment, the only way to be sure that 1 pulse per hour is not the noise impulse from the ladder, but it is the impulse from the test object that has to be taken care of. So there we have to learn much more in the field of DC, to my mind.
Okay, we're coming slowly on the final lap here of this round. And a question to all three of you. Of course, you're a lot in the very practical experience out in the field with PD measurements. What is your most remarkable experience here in the field? Uwe is...
Yeah, so I have there some insights I collected from the experts up front. Maybe we can show them a little bit also here for our colleagues joining the web talk. So here we see some practical examples how it looks like in the field to do high voltage testing, including PD measurements. So there was also this famous 400 kV AC cable in Berlin. That was one of the first XLPE cables where there also very intense measurements were done. Another example we see here are generators with huge diameters, and where you have then also to do very interesting tests and measurements on partial discharges. And another topic we can see here, how it looks like to measure then also at very complex structures like transformers. We got a lot of questions also regarding how to measure correctly at transformers. So, and you might wonder who is the guy with the black hair in the middle? Alex, it's you. And the same topic is also how to measure on GIS. There is always the question how you couple then the measurements, or how you can couple then also the measurement equipment then to the equipment in the correct way. So, but that should give you only a certain flavor of how it looks practically to do PD measurements.
Practical experience always welcome here. If you have examples, you can also send us pictures. That's clear. We're going in the final round here of the second web talk live from Dresden. Eric Winkelmann, localization of PD is always a hot topic, of course, as we discussed today, which was quite a very vivid discussion. What is the state of the art, and will we see better technical capabilities in the next future, in the near future?
So what I can tell to this topic is that from the cable view, you have the so-called TDR, the time domain reflectometry, which is more or less a reflection measurement to get your failure localization. And for transformers and GIS, you have the acoustic and UHF measuring technique to do a localization. But maybe, as I tried to mention a little bit before, one PD signal, so if you really look on the signal, should be enough to find out where it comes from, because everything is hidden in the signal. So I believe that there will be techniques and also possibilities to improve there in the future.
Thank you very much, Eric, for this final statement. To Alexander Kretke, the statement, integration of renewables, for example, electromobility, they are key elements in the Energiewende, the so-called Energiewende. It's a worldwide topic. Are there also new areas of applications where PD measurements are necessary?
Yes, one thing that we can observe more and more is that, especially for electromobility, the voltages that are applied during PD tests going down, so that the samples are smaller, the objects are smaller, and then we are testing not with 600 kV, but just with 600 volts. Because not the voltages is the important part, but the field strength, and especially in electromobility, where you have a lot of inverters and stuff with very sharp rise times, things that never have been tested for PD are now tested. Another example is traction transformers. Traction transformers for railway applications haven't been tested for PD since decades, and now it starts that even here this technology has to be applied. And another point is, for example, little dry type cast resin transformers haven't been tested at all for years. But with the application as let's say a GSU transformer in the wind farm application, smaller transformers became a higher importance, and now they have to be PD tested, which hasn't been the case years ago. So it goes down to smaller objects and smaller voltages, and the other point is that people have to start testing PD, which haven't been affected with that, and they don't have a high voltage background. They never heard about PD before, and I mean this is that's really a challenge when it comes to application know-how.
Some more necessity. Professor Plate, in Berlin in the late 90s, there was this really hype, you can say, about PD patterns interpretation with neural networks, neuronal. Will we see a revival of this approach with the enhanced AI algorithms?
Of course, big data and using artificial intelligence to interpret huge amounts of data will surely help also the field of PD diagnostics. But let me remain a little bit skeptic as an old man that we will not find a very simple solution. And to my mind, of course, it's very easy to take some PD data in the lab and then to apply algorithms. I think the scientific journals are full of such papers with numerous approaches and all claim to be new and perfect. And as soon as you apply them in the field with some real noisy situation, you can be sure that only a minor part of them will properly work, to my mind. Nevertheless, I'm quite optimistic that we'll see further progress, and we barely need it, especially for the field that was touched by Alex now, for Alex Kretke, that more and more power systems are driven by converters. And I think this is also worth to mention that PD measurement started with pure sine wave, 50, 60 hertz. And now we face converter switching rates in the 10 kilohertz range and very steep switching velocities. And the gradient of the voltage applied to inductive equipment, of course, gives over voltages in the equipment, even for low voltage equipment. And that is the major reason, to my mind, that the interest of PD will increase in such fields where we didn't take so much care of in the past due to new effects in the insulation system. We have higher power densities. The wind turbine transformers, traction transformers have special insulation system, high temperature insulation systems. They have
Yes.
partly higher field stress. So all these
Yeah.
will lead to higher demand of new solutions and better solutions that we have today.
Ronald, thank you very much. We're jumping in the last minutes of this web talk. It's an interactive format, and of course, all questions are asked by real humans, so artificial intelligence is not quite taking place here. Uwe.
Yeah, so I would like to switch into a completely new setting because we have not trained it before. So I would like to do the following. So we have a lot of very practical questions. So I would like to ask these questions right now and would like to ask our experts to give an answer in not more than 30 seconds.
Yes, absolutely.
Okay, so then the first question. Discharge mechanism is different for solid, liquid and air. Will coupling capacitor technique be reliable for all three dielectrics? Professor Plath, 30 seconds maximum.
Yes.
Thanks. How accurately can one locate a PD source in a large and complex equipment such as power transformers? First Alex, then Eric.
Depending where in the installation it is. Typically, we are lucky that the highest field stress and the highest voltage is on the outer part. So typically, you have a quite good chance to make it like something like a 10 centimeter diameter ball. But it depends very much. If it is deep in the middle winding, then it's much harder to get it.
Eric, something to add?
No, I would confirm this. I would say a football size. You can do it if you do a good job in a transformer.
I would like to add something.
30
if
seconds.
I'm allowed to. 30 seconds. So acoustic sensitivity is much lower than electric, and so we usually use averaging triggered on electrical signals. That is the proper method. And the problem is if we have not a stable trigger on one defect source, then that becomes more difficult. And I think we will see in the near future better solutions to average on single defects and to get better acoustic sensitivity for localization. Was it shorter than 30?
It was 24 seconds.
Okay,
Excellent.
Excellent. And another question.
Uwe?
Once I find partial discharge, how critical they are or how long will my isolation last? My answer would be, it depends. And your answer?
Yeah, give me 30 minutes and we can try to answer it.
Okay, you write a letter back.
Okay. No, but it depends really. So it's what we maybe discussed before. So you look on the value and on the pattern, and the value is not true, and the pattern is telling you anything.
And
We had decades of research, for example, the energy of partial discharge, you may remember, to link it to degradation processes.
Yeah.
This is extremely difficult and it depends, but there is some hope. I followed a PhD in Milano in Italy that took quantum chemistry to better understand the molecular level of degradation, and you can see this is very basic research. And but in the far future, I could imagine that our knowledge will increase even to predict better than we can today, because now it is really not very exact, not very precise.
Okay, next question. PD pattern derived after noise separation is more important than the PD level as such, especially for on-site measurement. So especially more if the background noise is very high. So I think, Alex, that goes a little bit also into your direction and experience. You can agree to that?
For me, it was a statement, not a question. So for me, I would say yes. It's absolutely right. And I say the point is when you, for example, look, you have to localize in an oil-filled equipment a PD source, and you have more than one source. Then the first step must be to look for noise separation or source separation to have a stable trigger to the acoustic system. So to look for that kind of defect, that kind of defect, or that kind of defect. And in that respect, the modern, let's say, digital technology has much better possibilities than we had in the recent years.
Okay, a cable question. Does the contaminant in insulation affect the PD value or lifetime of the cable? That's the question to Berlin.
Lifetime depends on the size of the particle and the field enhancement. So we call it electrical aging. That can last for decades before it leads to inception of partial discharge. And the other way around, if the particle will not cause in field enhancement at test voltage stresses that causes PD, we will not see PD. but we can still have aging. And that is exactly these parts of defects that makes us nervous as PD engineers, because we cannot find them during commissioning or during acceptance testing.
Okay, then
Excellent.
final question
Yeah.
to all three. In which way online PD measurement will support in future high voltage asset management?
Online measurement.
PD online measurement to support high voltage asset management. 30 seconds each.
Should I start? So
Yes.
first of all, I'm not part of any producer, but I would recommend worldwide at this situation to make more monitoring, not because we understand every detail in advance, but as Alex said, if we do not collect data, we will not get better interpretation in the future. So monitoring is quite cheap in contrast to the damage that can prevent it by monitoring. And so I would like to recommend to do it. And yes, that is a certain amount of money, of course. But if you look at the EHV level, I really do not understand why some utilities still hesitate to a large extent to use monitoring.
All right.
My transformer point of view, I see the tendency, especially for the Central European utilities, that they try at least to integrate permanently installed UHF sensors into the tank right from the beginning, to have the possibility to, if the DJA readings of the gas monitor set an alarm to hook up the equipment and then to monitor for a while, temporarily or permanently. The key point is to avoid false negatives, false positives. That's the point. So it depends on the importance of the equipment and the type of insulation material in the equipment.
Eric is fine with this.
Yes, I confirm, and it's not my real business, I have to say.
All right. So just to sum it up for a very short minute, and then I come over to Uwe. PD measurements, as we learned, ensure product quality, on-site installations and operation of grid equipment, digital solutions, pattern recognition, artificial intelligence. We talked about all this will further develop, of course, and new possibilities for PD measurements are upcoming. And I thank very, very much to Alexander, to Eric, to Ronald. And now my way is a long way over to Dr. Uwe Kaltenborn through this high voltage test hall. Uwe, because at the end, we invite you to join us next week.
Yeah.
Next, of course, you get later on a little gift from us. It's the Dresdner Frauenkirche chocolate.
Yeah. Right.
Yeah. And Ronald, you have to print it out with a 3D printer, a chocolate printer.
For the audience, I would like to make a home experiment in my home office. It takes only 1 second. Look, my high voltage generator.
Oh. Is this for killing flies?
No, yes, it's for killing flies and to keep me in your memory.
Very nice. Okay. Excellent. Yeah, we do this also in the next shows. We do more experiments like
live experiments. Yeah, okay.
Uwe, next week?
Next week,
Wednesday?
Next week, Wednesday, 5 p.m. And
worldwide?
We would like to talk then about on-site testing of cables, and that's exactly what you see in our bag. Yeah, this is the gray thing in the back. This is a truck trailer, and next week we will show you what's behind that and how we use that then also for on-site testing of cables.
That's a very good cliffhanger, as we say. Of course, everybody is broadcasting next week with us. We are live, and we are saying from this time from HIGHVOLT, Uwe, thank you very much. Thank you to our experts. Thank you for your questions, of course. And we say exactly at 6 p.m. Good night and goodbye from Dresden. Auf Wiedersehen.
Goodbye, thank you.
Goodbye.